In this video, we're going to talk about a type of process that we call a polytropic process. It's a process that we've kind of already run up against, but we're going to generalize it a little bit. So let's follow along as we first start out just looking at some things that we've done previously. What we said for an adiabatic reversible process here, we've said that the pressure times volume to the K is equal to a constant, right? Where K, if we remember, that's just a constant related to the heat capacities, Cp over Cv. Another way that we've written this was P1 V1 to the K equals P2 V2 to the K power. But remember, if that equation is the case, then it must be the case that P1 V1 to the K is just a constant throughout the entire process. We're going to generalize this to a general polytropic process, which is a process which can be described by the equation P V to the N power is a constant. Where N is just some number. So in our first case, an adiabatic reversible process, we have K, the ratio of the heat capacities, but now we say, well, let's let that be some other possible number too, maybe something that's not just the ratio of the heat capacities. When we had this first equation, P1 V1 to the K equals P2 V2 to the K, we see here, we had a whole bunch of other different versions of this equation that we could get between and kind of cycle between pressure, temperature, volume, temperature, using just ideal gas law things. So we can rewrite these same equations for polytropic processes. So we could write, for example, T2 over T1 is equal to P2 over P1 to now N minus 1 over N. Or we could write T2 over T1 is equal to V1 over V2 to the N minus 1. Or we could write P2 over P1 is equal to V1 over V2 to the N power. So the same equations that we used for adiabatic reversible processes, because we have essentially the same form of the equation. PV to the N is a constant. Using the same logic, we can kind of skip ahead a few steps determining work. We're going to use the same strategy that we did finding work for an adiabatic reversible process. So we have work equals the integral of P dV. We're multiplying by V to the N over V to the N. So that equals the integral of P V to the N over V to the N dV. Then we can take this out, right? Identify P V to the N is just a constant. So this ends up being P V to the N. That quantity is just a constant, so we pull out the entire quantity, despite the fact that V is actually changing. V to the minus N dV from V1 to V2. We solved this before, so I won't go into the details. But we can just write the answer. So then the work from 1 to 2 is P2 V2 minus P1 V1 all over 1 minus N. We could also rewrite this as, PV equals RT. So we could write this as R T2 minus T1 all over 1 minus n. So the same essential equations, that we got for adiabatic reversible processes, now we get for these processes that we call polytropic. Some examples of where you might find a polytropic process. It's any process where this quantity, PV to the n, is a constant. We could call a polytropic process. Some of them have specific names. One would be an isentropic process. That would be delta S equals 0. That's a process that we already know about. That's where this is an adiabatic reversible process where n is equal to k. We could have an isochoric process. That would be that the change in volume is equal to 0. And if the change in volume is 0, we know that that is a zero work process. So if we look at our equation for work just up here, it's a 1 over n term, as we can see up here at the top. 1 over n. So what that means is if n is infinity, then this ends up going to 0. Isobaric, that's delta P equals 0. Again, we kind of know how to already do this. We would find this with P delta V. So with P delta V, that's essentially just, no, not the top. That's just this top part of the equation if the bottom ends up going to 1. So we can do that. That would happen if if our coefficient n is equal to 0, right? Which makes sense. PV to the n, it must be a constant. So pressure is a constant already. So we take V to the 0 power. That equals 1 no matter what the volume is. So then our polytropic equation is true. A general polytropic is just one where P V to the n is a constant. N is some number. And we can actually use general polytropics to model a lot of different processes. So you could model, instead of an ideal system, we could actually use this to model real systems in certain conditions. We would solve it and actually do our calculations very similar to what we would do if n equals k, or if any of these other processes are happening, right? We just need to know what is the exact process, what's the pathway that we happen to be taking. The last one, which is a little bit different, is isothermal. So that's, as hopefully you know, no change in temperature. So PV equals RT. So if T is constant, then PV to the 1 is constant. So that's an n equals 1 polytropic process. And this one we get a little bit different. If we go and if I scroll back up, if we look at our solution here, we see that we would actually get, at this point, we would get V to the -1, or 1 over V. And then rather than kind of doing that as a power, we would do that. That's just, that integral is a natural log. So we can see if n equals 1, these solutions here end up blowing up to infinity, which is obviously not physical. So that's the reason, is because our integration step had to be different because of that step. So it's only different for n equals exactly 1. So if n equals exactly 1, then we can write P V equals RT. So pressure is RT over V. So then this integral is RT over V dV. Both of those tops are constants. So this is equal to RT times the integral of 1 over V dV. Which we know the integral of 1 over V, that's just a natural logarithm. So in isothermal process, the work is a little bit different. It's RT times the natural log of V2 over V1. We could also write this as RT times the natural log of P1 over P2. Or PV equals RT, so we could write this as P1 V1 times the natural log of P1 divided by P2. So all of these are exactly equivalent. We're just flipping variables using the ideal gas law. So this is only isothermal. And these are really going to be our last equations that we add to our equation sheet. You can pull up the final completed equation sheet to see how I've added it. But we're going to essentially add these series of equations for isothermal processes. And we're going to add these two equations up here for our general polytropics. With that, we should be pretty much set for our equation sheet. Again, pull up, there's a separate sheet posted where I've actually filled out all the way to the end of that equation sheet. So pull that up, add those equations now, make sure your equation sheet is totally filled out, and we should be all set. So that's all we're going to talk about polytropic processes. We'll have some examples. You'll see these pop up in the homework. So you'll know them when you see them.